Hello, everyone. In this video, we'll talk about the Gram-Schmidt orthogonalization process. This is a procedure that, given any basis for a certain vector space, will produce a modified basis which is furthermore orthogonal. So we'll start from any random basis and we'll get to an orthogonal one. This will answer the question whether any subspace of Rn admits an orthogonal basis. We know that every subspace admits a basis, and this procedure makes us jump from admitting one basis to having at least one orthogonal basis. So every subspace of Rn admits an orthogonal basis. Let's see how the procedure works. Maybe before doing that, I'll just draw a line, I'll draw a little scheme of what the idea is behind what we're doing. Well, first of all, we start with any basis. I'll just sketch the case in which you only have two vectors like here. You see that by the recipe here, if you start with any basis u1 through un, the first vector u1 is going to be the first one of my new vectors here. So suppose you have something like this. How do I cook up the next vector in my future orthogonal basis? Well, I'm supposing that I'm given a vector u2, which will look something like this, maybe. Now, the basis v1, u2 is not orthogonal here. To make it orthogonal, the idea is that of taking the projection of u2 down to v1, and that's this red vector down here. And what we actually want to do is, instead of considering u2, we will consider the vector v2, which is u2 minus its projection down to the axis. So this is going to be my new vector v2. You see now that v1 and v2 are orthogonal to one another. And the way we obtained that was to take u2 and modify it by its projection down to v1. Let me write that in a formula, and then maybe it will make more sense. So v2, my second orthogonal vector, will be given by u2 projected down to v1, and the formula for the projection is the following. There's this coefficient, and then that's multiplied by v1. That's the vector here in red is the red vector down here in this picture. Maybe I'll write it u2.v1 over length of v1 squared times v1. So 1. Okay, so that's the idea. From every one of the vector, I subtract all of the projections to the previous vectors until whatever is left is perpendicular to all of them. So that's how it will go for the new vectors after that. Now we have v1 and v2. To obtain v3, I need to start from my vector u3 in my basis in here, and then I will subtract whatever the projection is of u3 from v1, which is this quantity here, and I will subtract also the projection of v3 onto v2. So that's how it works until the last one of the vectors. We modify all of them by subtracting the projection of the initial vectors ui's onto all of the v1s that we have created until that point. So the last vector vn will be the projection onto all of the previous vi's. So I will project stopping at the vn minus 1 vectors. So that modification will give me my last vector vn. The output of this procedure is the set of vectors v1, v2, v3, all the way up to vn. And what is magical, I mean, it's not magical, this procedure is made to work. These outputted vectors are orthogonal between one another. So they make up an orthogonal basis if you started with a basis u1 through un. Let's have a look at an example on how to do this in practice. Here's a basis of a subspace of R4. It's a subspace U of dimension 3 inside R4. Let me give names to these vectors. This is going to be our U1, this is my U2, and this is U3. Now, if I want to turn this into an orthogonal basis, I'll do the following. V1 is U1, so I will start not changing the first vector. The second vector, V2, will be U2, to which I have to subtract the projection of U2 from the previous vector, V1. And that's the following quantity. So let's put numbers to all of this. U2 is 0, 1, 0, 0. Sorry, 1, 0, 1, 1. It's exactly the opposite of what I said. Then here we have to compute U2 dotted with V1. V1 is equal to U1, so we can compute the dot product up here. We get 0 times 1, 1 times 0, 1 times 1, and 1 times 1. So that becomes a 2. The length of V1, which is equal to U1, is the square root of 3, just by summing the squares of its entries and then taking a square root. And this is the coefficient in front of the vector V1, which is 0, 1, 1, 1. In other words, when I write V2, I mean to write the following vector. We have 1 minus 0, that's the first entry, and we have 0 minus 2 over root 3, and we have 1 minus 2 over root 3, and then we have 1 minus 2 over root 3. That's my vector V2. I can clean it up a little bit and write it as follows. 1, 0, 1 minus 2 over root 3, and 1 minus 2 over root 3. Now you can check that V1 and V2 are in fact orthogonal. Yeah. Okay. V3 is the next thing that we need to compute. I'll write down first its expression. This is going to be the vector U3, but modified by the projection of U3 onto V1 and the projection of U3 onto V2. Okay, let me double check that these numbers are correct, and then we'll complete the computation. Of course, there's a few mistakes in this computation here. First of all, the length of this vector should be squared, so I don't need to take a square root there. The length of V1 squared is just the sum of the squares of its components. And I think I wrote something down slightly incorrectly here. So this is 2/3 and 2/3. 2/3 and 2/3. But this is minus 2/3. So when I want to clean this up, I have 1 minus 2/3, which becomes 1/3, and 1 minus 2/3 also becomes 1/3. So this last vector here is 1, negative 2/3, 1/3, and 1/3. Okay, sorry about that. This is the result for V2. And in fact, now you can actually check that V1 times V2, dot V2 is equal to 0. It didn't work before. Let's move on and do the third vector, V3. So we wrote down the formula correctly. Now let's put numbers to it. U3 is -1, 1, 0, 1. Then I have the dot product of U3 times V1. We can look at that up here, and we have U3 times V1, which is U1, becomes 0 plus 1 plus 0 plus 1. So I can write that 0 plus 1 plus 0 plus 1. And let's have a look at the length of V1. That we already computed, and it's equal to 3. We used it in the previous computation. V1 is the vector 0, 1, 1, 1. Then we compute the dot product between U3 and V2. U3 is here and V2 is here. So let's dot them together. What we get is -1 in the first term. Then we have -2/3. Then we have 0 and plus 1/3. Then we want to divide by the norm of V2. And maybe let me compute that in an aside here. The norm squared of V2 is equal to the sum of the squares of its components. So it's 1 plus 4/9 plus 1/9 plus 1/9. And when I add these together, I get 9 plus 6 is 15/9. And we now have the vector V2, -2/3, 1/3, 1/3. Okay. Let me move this a little bit more out of the way and continue with this computation. We have -1, 0, no, -1, 1, 0, 1, minus, we have 2/3 times this vector. So that becomes 0, 2/3, 2/3, 2/3, minus what we have here is, well, let's see, at the top is -4/3 divided by 15/9, which is the same as multiplying by 9/15. So we get a 3 here and nothing there. And this becomes a 5. So we get 4/5 times the vector that is in there. 4/5 minus 2/3 times 4/5. And that's, well, we'll write it in a second. Here we have 4/15. That's a third times 4/5. And 4/15 is the last entry. Okay. Now we can write down our final answers here, or get close to it at least. We get -1 minus 4/5 is the first entry. Then we have 1 minus 2/3 plus 8/15. And then we have minus 2/3 minus 4/15. And 2/3, oops, again, minus 2/3 minus 4/15. I'll pause the video for a second to double check these numbers. There was one slight imprecision. We computed correctly that this number was -4/5. So this sign here needed to be changed to a plus, and therefore I will have to change the signs in here to get a plus and then a minus, plus, and plus. And one slight thing, there's a 1 down here. The rest is correct. So when we draw these sums together, the result we get is the following. The first one is minus 1/5. Then we have the second one. Well, if you compute it, you should get minus 1/5 as well. The third is minus 2/5, and the third is 3/5. You can double check these numbers later, but they come from those sums there. Okay, so let's wrap this up. We have these new vectors here. So the newly found orthogonal bases will have vectors 0, 1, 1, 1. This is one of the ones that we started with. Then the second vector will be what's written here. That's going to be we called it V2. And the third vector, V3, will be this vector here. This basis is now an orthogonal basis of the subspace U inside R4. Okay, it's a little bit of a lengthy computation and it needs to be done with care. So I recommend that you double check your computations every time you do this. There's an easy way to check that your result is correct, and it is to compute the dot product between the vectors you got. Everything in these dot product should be 0. If something is not 0, then it's a symptom that some computation may have gone wrong. I'll see you in the next video.